Okay, so let's do some examples now. So here's that famous Haber process again, nitrogen and hydrogen coming together to make ammonia. Hopefully you can see that this is saying kilocalories. That's the older unit. We use kilojoules now. But the fact that it's over here on what we call the product side, this is an exothermic reaction. The other way we could write it, remember, is we could see it outside of an equation. We could see a negative 22 kilocalories. So that's another way to illustrate it. So I want you to be able to understand both. I would always recommend that you put it in the equation. It just helps you to understand better. So that way you can treat it as a reactant or a product. All right, so this is how this little worksheet's set up. It says we are going to add N2. Well, N2 in our reaction here is a reactant. And we're increasing a reactant. So if you increase the reactant, the equilibrium is like, oh no, I can't have that much N2 in this container. Because remember, all these are in the container at the same time. I need to make that N2 go away. Well, the only way you can make the N2 go away is to react some of it with hydrogen and make more ammonia. So we're going to see the equilibrium shift. Now it's still equilibrium, so you get little tiny, big arrow, little arrow, but still we say it shifts to the right, so that's what you're seeing here. And so we say shifts right, shift to the product, whichever you prefer. So shifting to the right is what they say. So that means everything on the right of the arrow, everything on the product side is going to increase. And so that's why we're seeing the word increase for this product here. And everything on the reactant side is going to now decrease. Now we have a dash here for this one because that's our stressor. So we don't usually answer the question on the stressor. It's going to react until this guy does go away. So technically it's going to decrease after we've increased it. But nothing's going to affect our K unless we've got temperature change, and this is not a temperature change, so there's no effect on the K. So the constant stays constant as long as we're not changing the temperature. All right, we're going to add H2. That's again a reactant. So it's going to cause, we're adding a reactant. That's going to cause it to shift over to the product side, which is to the right, and you can just write R. Or you can say shift to the product, that's fine. That means the products are going to increase. So we're going to see that increase here. And then our reactant, not the one we stressed because that was our stressor, that's going to decrease. So we're going to see this decrease. Well, what's going to happen to the constant? Nothing. It's going to remain the same because that's not a temperature. All right. So now we're going to add ammonia to the system. So we're adding ammonia here, so our additions here. This is a product. It's like, oh no, I don't want that much ammonia in my system. I need to be back to equilibrium. So we're going to shift to the left. That means everything to the left of the arrow, meaning on the reactant side, the reactants are going to increase. And this is going to stay the same. Number 4 says we're going to remove. All right, so now we're going to take some stuff away. We're going to create a void. So how do you take care of voids? Well, you've got to fill a void, right? So I'm going to remove some N2. I am removing a reactant. Oh, what happened to my A there? I'm going to remove some of this. So I'm going to take some of this away. So I need to fill this hole, this void. So I'm going to shift that direction. So you always shift towards the removal side. So I'm removing that. So I'm going to shift to the left. What's going to happen to this guy? Well, it's going to increase. What's going to happen to this guy? Well, it's going to decrease. What's going to happen to the K? This is not temperature change, so it's going to stay the same. Okay, this is not hard. All right, so let's look at the next one. Number 5, we are removing H2. Is that a reactant or a product? We're removing a reactant. So if we remove a reactant, it needs to fill this hole, so it's going to shift towards that. So it's going to shift to the left. So what's going to happen to the N2? Well, N2 is going to increase. We've lost the top of our chart there, but that's okay. This is the NH3, so this is going to decrease because the arrow is pointing that way. And what's going to happen to our K is going to stay the same. This one we are removing. Keep that. Okay, we are removing NH3. So we're going to remove a product this time. So if you take some product out, it's going to shift to make more product. This is one of the ways they keep making ammonia. They keep taking it out and they keep shifting this. So we're going to shift it to the right. And so what's going to happen to these two guys, they are going to decrease, decrease. So we're going to see a decrease, decrease, and this is going to stay the same. Okay, I'm hoping you're catching on that this is not too bad. Got a little circle around my H2 there. All right, so now it says increased temperature. So now our an increasing temperature. This is not temperature, but it's a measure of energy. So you can use it in the equation. So you're increasing temperature, that means you're increasing the energy. So I am increasing, and because this is exothermic, it's a product, so I'm increasing on the product side. Just like over there, if we increase on the product side, we are going to cause it to shift to the left. If we go to the left, everything to the left of the arrow is going to increase. And what's going to happen to this guy? He's going to decrease. And do you remember we go products over reactants raised to the coefficient power? Well, this is like a really big change. You mess with the temperature, so you completely mess up the equilibrium. It's kind of like if my husband said, hey, we're going to move to Tyler. Well, that's okay. Temperature's about the same. Not really going to mess up my equilibrium. I'll have to do some things to kind of figure it out. But hey, if he says, hey, we're going to move to Antarctica, well, that's going to mess up my temperature, and that is totally going to mess up my equilibrium. My constant can't ever get back to the same if we're moving to Antarctica. So it's like a huge difference. So the best way for me to say is what's going to happen to the constant, it's going to be whatever the products are doing, because the products are on the top of our equilibrium constant. So if the top is decreasing, the products are decreasing, you are going to see your K also decrease. And if you think about it, it makes sense, because the smaller your K, the more your reactants are favored. So these two are always going to match. So whatever your product's doing, K is also doing, but only with temperature. Temperature is the only thing that makes a difference in that. All right, so now you should maybe figure this out. They are decreasing the temperature, so we're making it colder. So we are lowering on the product side. We're removing technically energy. So if we remove, hopefully you can see we're going to shift to the right. If we shift to the right, what's going to happen here? We're going to get an increase of NH3. So what's going to happen here? It's going to match because we're dealing temperature. What's going to happen to these two guys? They're going to decrease as well. So not too bad. Let's see if the next one has. All right, good. So number 9 and 10, still the thing going on. We've got pressure. Anytime you increase pressure, if pressure goes up, volume goes down. So they're opposite. So volume going down, and if you think of volume as space, space is the best way. So if you increase the pressure, the only way, that means that you're giving it less space. It always favors the side that's going to make less moles of gases. Only gases, because that's the only thing we care about. Less moles of gases. So we've increased our pressure, so we want to shift to whatever side has the less moles of gases. So up here, there you have 4, and here we have 2. So increasing that pressure, it's kind of like if you get too much pressure in your life, you want to be around fewer people. Works out. If you have less volume, you want to have less people in that volume, right? So less moles of gases, so this is going to shift to the right. If we go this way, what's going to happen to this guy? We're going to get an increase of him. What's going to happen to these guys? We're going to get a decrease. And this, we're assuming pretty much Boyle's law that temperature is not being changed here, so we're going to say it stays the same. So unless it says the temperature is changing, we're going to assume that it's staying constant. So you can pretty much see if we decrease the pressure, you don't have as much pressure on you, you're going to favor the side that has more moles, trying to equalize that pressure out, more moles. But again, it's just gases, so it would shift to the 4, which is to the left, and you're going to see more N2 and H, kind of like you don't have much pressure, you have more friends over, and so we're going to get an increase of those reactants, we're going to get a decrease of that product, and this is going to remain the same. Alright, so your little worksheet is kind of like that. It shouldn't be that bad. Again, hopefully this makes sense to you. If not, come see me.